All right. So I guess we can talk about real quickly about some of you have started on the homework, and we've seen people post messages about trying to get it compiled and get it build. Has anybody not tried to download it and not tried to even like fork the repository? All right, everyone's at least tried that. Okay, that's good. All right. So the other thing to announce is that Zuchang Lee is still in the hospital after being shot last week. He sent me an email this morning that he wanted me to read to you guys real quickly. It says, "Dear 15/7/21, I'm sorry that I still can't make it to class. I'm still laid up in the hospital after those fool DBA shot me. I do not want any of you to take revenge for what happened to me. I don't want any more bloodshed. I know who did it, and they will pay. Databases are a rough game, and I knew that going into it, but snitches get stitches." And he has a big shout out to my crew, Reeks, Westbred Diamond, and DZZ, and he signs it Zuchang. So those of you know who you are, you get the shout out, so he's in our thoughts. And I got a get well card for Zuchang that I'll pass around so everyone to sign it, and we'll hand it to him when he gets back. So hopefully he gets better real soon. I don't think it's serious, but it's just, I don't have a pen. It's not serious, but like again, it was pretty traumatizing. It was pretty unexpected. So okay, so last week we talked about in-memory databases as like an introduction to as a way of distinguishing them to be how they're different than disk-based database systems. We showed that if the database system makes the assumption that the primary storage location of the database is entirely in main memory, then all different facets of the database system architecture ends up having to change, right? We don't have to manage a buffer pool anymore because we're not going to be swapping things in and out of disk, right? We may not want to use a heavyweight concurrency control scheme because the stalls from transactions are going to be very small, right? Because we're not going to have to wait for a big page fault to go fetch things back in, right? So now, starting today, and for next week, we're going to start, and for the rest of the class, we're going to start talking about one by one the different components you need to have in a database system to be able to support fast transactions and analytical queries at the same time, right? So we're going to start off with what I think is the most important topic in a database system, and that's its concurrency control scheme, right? This is going to allow us to be able to run multiple operations at the same time and be able to support a large number of concurrent activities going on in the system. And so for today's class, we're going to start off talking about just like an introduction to different transaction models that you could have in a system. And we're going to go a little bit deeper than what you may have learned in like an introduction database course. And then from then, we'll talk about sort of a high-level overview of what a concurrency control scheme does and what the protocol provides for a database system. And then we'll finish off talking about the paper that you guys all read about doing an evaluation of these concurrency control protocols on a CPU with a lot of cores, right? And I realized this was a simulation CPU, right? You can't buy a chip today that has 1,000 cores, but the idea is that by scaling it up to that high core count, we start to see how things start to fall apart. And then eventually, when these cores come along, we'll have to reevaluate how we do concurrency control, okay? All right, so this is, boom. So before we get started, let's first define what a transaction means. So everyone here should have taken an introduction database course. So every one of you should be able to define, give me a definition of what a transaction is in the context of a database system. So anybody like to take a shot? A one-sentence definition of what a transaction is. Come on, some of you I know were in 615, right? Right, good, excellent. So my clicker is not working today. That's all right. We're going to say again, almost basically exactly what he said. A transaction is going to be a sequence of actions, and I'll add that this piece that he missed, that they're executed on a shared database to perform some higher level function, right? And the part that he brought up was that all the actions in a transaction have to occur or none of them occur, right? It's the basic unit of change that we're going to have in a database system, so we're not going to allow partial transactions, right? So if we go sort of this definition to the three main parts, right, we're going to say that's a sequence of actions, and we'll define what actions is in the next slide, that are executed on a shared database, right? So we'll have a singular database instance. It doesn't matter whether that database instance is across multiple nodes, across multiple machines, across multiple disks. It doesn't matter. It appears as a single logical database to the application. And then they're going to perform some higher level function. So we're not talking about reading and writing for a single object or reading a page from disk or whatever. We're talking about some higher level activity that's going on in the application, right? Like adding money to your account, transferring money from one account to another, right? Friending somebody on Facebook. These are the high level actions or the high level operations that we'll care about. So we can define the actions a little bit further, and we'll see how we're only going to focus on certain ones when we talk about concurrency control. So we have three categories. We have unprotected actions, protected actions, and real actions. So unprotected actions are things that the database system is going to be doing internally that are not guaranteed to be fully ACID. They only can ensure that the database will be consistent after you perform this operation, right? So let's say that we are going to write 5 pages out to disk, right? That's not considered a protected action because any one of those page writes could fail. But the database system has to make the illusion that it can overcome that problem if it occurs. The reason why we say it still guarantees consistency because if you say write a page to disk, the disk controller will be able to guarantee that that single page write should be atomic, right? And so therefore you won't have torn writes and things like that. But that's on a single action level. Protected actions are the things that we usually think about when we think about transactions. Right? These are like the SQL queries. These are the high-level logical operations that the database is doing on behalf of the application. And they're not going to externalize or expose any changes that these protected actions make to the database until that transaction commits. Right? So the canonical example everyone always uses is you're transferring money from one account to another, right? From my bookie's account to my account. Right? That's 2 actions that occur, 2 unprotected actions where we're going to first debit money out of my account and then credit money to the bookie's account. The protected actions are occurring in the context of the entire operation, and we don't see any case where anyone can come in and do a read and see that there's money missing, right? The database system is going to protect that. The last one are what we'll call real-world actions or real actions. These are things that are outside the sphere of control or the scope of control of the database system, and we simply can't do anything about this, right? So this is things that occur in the physical world that the database system can't roll back. Right, let's say that you have a transaction and then halfway through you send an email out to a customer and then you try to abort that transaction. That email's gone. You can't roll back that change. You can't have that email be recalled. So these are the things that we normally don't put inside of a transaction, and we leave this up to the application to make decisions based on whether transactions succeed or not before they fire off these kinds of things. So we're mostly going to be focusing on the first 2. And you kind of think of the first one as the physical operations, and the second one are the sort of logical operations. So now, given we have a definition of transactions, and given we have a definition of the actions that are going to occur within a transaction, let's talk about different transaction models. So we're going to start off by reviewing flat transactions. This is what everyone thinks of when they think of a transaction, or you take a database course. This is the first thing we always teach you. And then we're going to show how this has limitations, and we'll show how to expand what flat transactions can actually do and see that some more complicated things that a database system can provide. So again, the flat transaction is what you learn in an introduction database course. It's the standard model where you have a begin statement followed by a sequence of operations or actions, and then there's either a commit or a rollback. And so in this case here, this transaction 1 wants to do a read on A, write on B, and then it invokes the commit command. And then what will happen is the database system will ensure that that write on B is now durable in the database, right? So no matter what, if we crash, if we fail, no matter when we come back after we call commit and get an acknowledgement that our transaction committed, we will always see that write on B. In the case of transaction 2, he does a read on A, write on B, and then he invokes rollback. And this basically is going to say that the database system will roll back any changes that this transaction made, and it'll be as if this transaction never occurred at all. Right, so we'll roll back in the write on B2. And so one of the things also to be mindful of in transactions is that a transaction could get rolled back not just because the application invoked rollback. The database system will be able to decide that I can't let this transaction commit because it'll violate ACID guarantees or violate the serializable order that I'm trying to enforce. So the transaction may want to commit, but the database system will end up rolling it back because it would violate that serial order. We'll see that more when we talk about concurrent control schemes later on. Okay, so flat transactions are nice. The majority of applications that are out there are written using the flat transaction model. But there are some limitations in some corner cases where it's not appropriate or it can't fully capture the thing that the application is trying to do, or the concept the application is trying to do. So the first problem is that an application can only roll back a flat transaction in its entirety. You can't say, all right, here's a bunch of stuff that I wanted to do, and then this last thing, I don't actually want to do it. I want to roll that back, but keep all the other stuff. Or let's say I'm going to update 100 tuples, and on the 99th one, I realize I made a mistake, and I don't want to update that last tuple, and I want to roll that back. I can't do that in a flat transaction. I have to roll back the entire thing, and then restart it and apply the changes to the other 98, 99 tuples that I'm trying to update. So there's no partial rollbacks. The second problem is that, so related to this, is that all of the work that a transaction does is lost if the database system fails or the transaction fails to finish. So again, if I'm updating 100 tuples, and when I get to the 99th one, someone pulls the plug on the power, and my database crashes, all of the work that I did is essentially wiped away. Right? And then you think, oh, 100 tuples, that's not big of a deal. But what if you scale it up to 1 billion tuples, and your transaction could take hours? Right? So all that work you did is lost because it's either all or nothing with flat transactions. And then the last point, which is sort of a nuanced point, is that a transaction has to occur in a single point in time. So you have to know exactly all the things that you're going to want to do at the moment when the transaction starts. Right? At least you can invoke all the things you want to invoke when the transaction starts, and you can't sort of stop the transaction and come back and pick it up later on. Right? So these are all the problems. And so you say, all right, what are some examples where these limitations are inhibited by flat transactions? And the two ones that are always given are one, or an application that wants to do multi-stage planning. So if you have to, say, maybe book a trip from Pittsburgh to Bologna, Italy, there's no direct flights from Pittsburgh pretty much anywhere, but especially not to Bologna, Italy. So therefore, you have to make multiple reservations. And you want to do this in the context of a transaction. Right? You want to book your flight from Pittsburgh to JFK, from JFK to Rome. Then maybe you book a train up to Bologna, or then rent a car. And you want all of these reservations to occur, or none of them to occur. Right? You don't want to book your flight from JFK to Rome, then realize you can't get on the train up to Bologna. Right? So you want to do this in the context of the transaction. And you can't do this easily in a flat transaction because you'd have to maintain all the locks and the reservations across from one stage to the next. The other big example that is always put out there is the ability to do bulk updates. So again, let's say you have a database that has 1 billion records, like you're a bank, you have 1 billion customers, and you want to update everybody's interest to increase it and rectify some error. And you need to do this in the context of a transaction, right? No customer should be able to see that one customer had an increase in their interest rate and they didn't, right? Everything needs to happen atomically. So again, the problem with this approach is that if we use a flat transaction, is that the transaction could take hours to do all the updates, get to the very last one, someone pulls the plug, and then we have to roll everything back. Another problem is that while we're doing this, we're essentially locking the entire database as we do this update. Right? Because if anybody comes and modifies things that before we updated it and after we updated, we'll see that there's a conflict, and we'll have to end up aborting our transaction and rolling it back, or we basically shut down the entire database while we do this modification. Right? This is a lot of times you see this in banking software. They'll announce that the website's going to be down on Sunday morning at 3 a.m., and that's because they're basically shutting the database down to do maintenance and do kind of update operations like this. So flat transactions aren't going to work for us. So we have to look at different models, more sophisticated, more complex models. And I'll say that, and I'll tell you as I go along, not all of these models are supported by all database systems. For the SAVEPOINTS and the nested transactions, most database systems support them. Compensating transactions and SAGA transactions are a little bit more complicated. And so not, again, like Postgres and MySQL probably don't support these things, but some of the more commercial guys that are expensive probably do. OK, so let's talk about SAVEPOINTs. So the idea of a save point is that we want to save the current state, the current context of a transaction at some point in time, and then provide a handle to the application that allows them to refer to that save point later on. Right? And so sort of think of this as like a mini commit or a mini rollback. Right? But you're not rolling back the entire transaction. You're only doing it for that sort of snapshot within the transaction's lifetime. And so the idea is that you can tell it to roll back and revert all the changes to go back to the previous save point, or you can tell it to release it and essentially just release all the metadata that it's maintaining about the save point. So to help you understand this better, I can show an example. Let's say we have a transaction here. It wants to do a write on A, a write on B, and a write on C. So when it starts off, every database system will do this that supports save points. So when you start a new transaction, when you call begin, this implicitly creates a new save point, whether you reference it or not, right? Because this is essentially storing all the metadata about what your transaction read and wrote, right? So then it does the write, and then that sort of gets put into the context of the save point here. And then now we'll say, we're going to reference and say, well, now we want to use save point. We want to refer to all the changes that we've done so far as save point number 1, even though internally it already gave it an ID. But this is now an ID that can be referenced by the application. Like you can give it a name in Postgres, or you don't have to always use numbers. So when we tell the database system that we want to create a new save point, this implicitly creates the next save point for us, right? So then when all the next changes come along, these are now put into the next one. And then we get to this guy here, and now he says, I want to do a rollback to 1. This essentially blows away all the changes that this guy made in save point 2 and reverts the state of the database back to save point number 1 here, right? And then implicitly, it also creates save point number 3 because we have to make a new one for any changes that come later on. So this does the write on C, and then it lands there. Now when we do a commit, the only thing that will be that actually gets written to the database will be the modifications to A and C because we rolled back the change that was made to B. All right, is that clear? And again, the database system is doing this automatically whether you invoke the save point command or not, right? Look at the more complicated example. So now we have a single transaction. It's going to do a write on A, write on B, write on C, and write on D. So the same thing before. We start a begin. We get a new save point. We do a write on A. It lands on there. And then we'll keep going down. And for every modification, we're just going to make a new save point, right? And then we get to here. We tell it we want to release 2. And what release does is it tells the database system that I'm never going to have to roll back to that save point, so don't maintain the metadata for it. So it blows away the save point metadata, but it still maintains all the changes that it made to the database, right? So it's different than the rollback. The rollback would revert the changes. This is actually maintaining the changes. It just, again, the extra stuff it's keeping for bookkeeping is thrown away. So then we do our write on D, and that lands on the last save point. Then now we try to do a rollback on 3. So the question is, what should happen here, right? Turns out the way save points work is they're sort of linked together. So when we told the database system we wanted to roll back 2, this implicitly also, when we told the database system we want to release 2, this implicitly also causes us to release save point number 3. So this would end up being a failure. The database system would not know how to roll back to this save point because it doesn't exist anymore, right? Again, the key thing here is not when we roll back and releasing things, we're still in the context of our transaction. We still have to wait until the transaction commits, but internally we can have intermediate states and that we can roll back to and release as needed. Is that clear? Yes?
So that means, this is like when you say release 2, you mean release everything, including it after 2.
Right, and so yes, and this is my save point number 4. I should maybe mark this. This exists, but the application doesn't have a handle to it yet. So it doesn't get released when you release 2 because
it didn't exist at that point.
It does exist at this point. Oh yeah, well, yes, you're right. When you release 2,
at the point of release.
Yes, and when you release it here, it didn't actually exist yet. Actually, no, it did exist because you did save point 3. So internally it creates it, but it doesn't have a handle yet. So the database system doesn't know what you're going to refer to this save point as, so it can't release it. If I roll, instead of releasing 2, if I rolled back to 2, then it would blow away D and blow away C.
So why this semantics?
Why would you want this? Think of that again, that example where I'm doing a bunch of modifications, and then I realize after I did one, I didn't actually want to do it. I want to roll that back, but I don't want to roll back everything else. This allows you that control. Yes?
When you release 2, are B and C included in the save point 4?
The question is, when you release 2, are B and C included in 4?
So,
That's a good question. I would think yes, actually. Yeah. Well, we can pop up Postgres and try it afterwards. Yeah, I actually don't know the answer, but that would make sense. Okay. So another variant, sort of applying the same idea of being able to have these sort of batches of transactions that you're splitting up operations to these batches that you can then control independently, transaction chains or chain transactions are basically the same idea as a save point, but instead of having all the modifications still in the context of a single transaction, it's now broken across multiple transactions. And what happens is when a transaction calls commit and it finishes, it atomically starts the next transaction in the chain. So you can think of like the commit and begin as being a single atomic operation rather than two separate ones. Right? And the idea is that because this is atomic, no other transaction can cut in between this and modify the state of the database. Right? It's sort of carried over to the next transaction. Right? And so the reason why it's different than save points is that when you do a commit as opposed to a release or rollback in a transaction with save points, the database system will free all the locks and all the latches that the transaction was maintaining. So when you go from one transaction to the next, it's a full commit. It writes everything out to the write-ahead log, it releases all the locks and latches that it holds, but then it just immediately starts up the next guy without having another guy be able to cut in between. Another thing is that you're not going to be able to roll back between different transaction chains. Right? So if I commit 3 transactions and the last one rolls back, I can't roll back the other ones. We'll see how to get around that in a second. But here's the basic idea. You have 3 transactions, 1, 2, and 3. When this guy commits, it immediately starts the next one. He commits, immediately starts the next one. And then this guy rolls back, but it only rolls back this modification to C. It doesn't roll back the modification to B, A and B. Is that clear? Again, I'm not sure how many database systems actually support these semantics. Yes?
What happens if transaction 2 goes back?
So let's say I do transaction 1, I commit, I get to transaction 2, he rolls back.
Transaction 3 never gets executed.
Yes, correct, yes. Again, you could define it based on what you want to do. You might be able to say if I roll back, then immediately still fire off the next guy. When we see sagas in a second, you'll see that it's not the case. If you roll back, then you start rolling back everything else. Okay. So another more complicated model that actually is supported in a lot of systems are called nested transactions. So before we saw that save points are going to be a sequence of actions that can be rolled back individually. In a nested transaction, we're going to have a hierarchy of work. Right? We'll have a transaction inside of a transaction inside of a transaction. And each of those inner transactions can commit and roll back independently, but their final outcome is dependent on the outcome of their parent. Right? So if we look at this example here. So I have a single transaction here, right? And the scope of the transaction is is encompassed by the top begin and the bottom commit statement. So we have all these inner guys here. So when the database system starts executing this transaction, you can think of this arrow as like the program counter. It starts off by doing a write on A, but then it hits this begin statement, and this is a nested transaction inside of the context of our global transaction. So this will create a sub-transaction, we'll say 1.1, and we'll essentially just move all the operations over to be now inside of this guy here. And then he fires off, he does a write on B, then we get another begin statement, and then we can have a sub-transaction 1.1.1 that again gets all the operations that are occurring on here. So now this guy will get to this commit statement, and it'll finish. It doesn't release any of the locks that it held because it's still in the context of the global parent transaction, right? But then we come back to our control for its parent transaction here. He does a write on D, but then he does a rollback. And that's going to roll back the changes of B and D and C. Right? So even though this inner transaction said he wanted to commit, its parent transaction says, I want to roll back. So everything gets rolled back. And then our control comes back to here, and then we do a commit. And therefore, the only operation that gets persisted is the write on A, because this whole sub-transaction here got rolled back. I know MySQL supports this. All the commercial database systems support this. You can emulate this with save points in some ways, which is sort of complicated. But I would say this is probably more common than save points. And a lot of database systems actually support this. OK. So these other transaction models we talked about so far, they're nice and all, but they don't solve our problem that we had before with the bulk update. We can use save points. We can use nested transactions to be able to do the multi-stage planning. But if we still have to update a billion things, all of these models don't actually work. And chain transactions seem like the right idea. But again, we sort of the problem that he brought up is if one of the transactions fails, we have to know how to roll back the other ones, because the other ones are allowed to commit. Right? They commit independently. And if a guy later down in the chain rolls back, it doesn't go cascade back to the other ones. So one way to get around this is that you could write in your application additional logic to check to see how many transactions you've executed so far in your chain, and then with one of them rolls back, you figure out how to roll back all the other ones. But now this means that you're maintaining the state of transactions in your application. So you're managing transactions outside the application and inside the database system itself, which is usually a bad idea, because the database system always knows what's best for your application. It always has the best view of what's going on inside the database. So chain transactions aren't going to be what we want to do. And so we have to figure out, the first thing before we can solve this problem, we have to understand how to roll back things correctly. So there's this idea called compensating transactions, where the idea is it's a special type of transaction that knows how to reverse the actions of a previously committed transaction in a correct manner. And by correct, I mean we're going to have to do this reversal in a logical way rather than a physical way. Can anybody tell me what I mean by this? Right, say we have an example, right? We have a transaction that every single time it commits, like say every single time somebody enrolls in the course, there's a counter that says that the number of students that are enrolled, and we always want to add 1 to it. Why do we have to roll it back logically instead of physically?
So that we can omit some implementation level details.
So this statement is, so you can omit some implementation level details. That's sort of true. Yes?
What if you failed when you're doing a rollback?
The question is, what if you fail during the rollback?
So that if you keep track of all the rollbacks, if it fails,
Right, so you could tell the database system that if my rollback fails, and it fails for a non-hardware failure, if it fails because it aborted because of a conflict in the concurrency control scheme, always retry it. Right, you could tell the data system to do that. I'm looking for something a little more high level here. All right, so I have 10 people. When I enrolled in the course, there was 10 people, right? So I was person number 11. So when my transaction ran the first time, I took the value 11 from 10, added 1 to it, and stored that. Then I realized later on I need to roll back that transaction. I got kicked out of the course for whatever reason, and I need to revert that counter back to what it was before. But between that time, 5 other people enrolled in the course. So now the counter is 16. So if you do it at a physical level, I would look in the write-ahead log and say, well, when my transaction ran, the original value of this counter was 10, and then now the new value that I overrode it was 11. So when you go try to do compensating transaction to roll it back, you would see the original value was 16, but then you would put the value back to 10, right? Because that's what it was before when your transaction ran the first time. Yes?
Can't you do something like get rebase?
His statement is, can you do something like get rebase? It's an interesting way to think about it. It's sort of the same thing, yes. So what you really would do when you do is logically is, and I actually don't know fully how get rebase actually works, so we can talk about that later. But what I mean is again, the physical thing would be take the original value and overwrite it with the current value. Logically would just be take the current value and subtract 1 to it, right? That's the difference. So that's what you have to do in a compensating transaction. So it's not simply just rolling back what you did the first time you ran. You have to write some additional logic to actually understand what the state of the database is and how to correct it, right? So now, if we have compensating transactions, we can now do what are called SAGA transactions. Right, so this is an idea that was proposed in the late 80s by Hector Garcia Molina, and that was the guy who wrote the paper you read last class for the main memory stuff, right? And the basic idea of a SAGA transaction is it's going to be a series of chain transactions that we're going to want to execute one after another. But then if one of those transactions fails, we'll go in reverse order and execute compensating transactions to reverse the changes that we made. Right? So you can think of it as if you have a series of transactions, T1 to Tn, and then corresponding transactions, C1 to Cn minus 1. And why is it n minus 1 and not n for the compensating transactions? Because if the last guy completes, then we're done. Right? We never have to roll back the last guy. So we're going to say that with SAGA transactions, we either want to have we want the database system to guarantee that we'll commit all our chain transactions T1 to Tn in that order, or we will commit transactions T1 to Tj, and then there's some kind of failure, and then we'll go and reverse order the compensating transactions from Cj back to C1 to put the database state back where it was before we started our transaction chain. Yes?
So you said you need logical rollback because If something happens in between.
Yes.
If you're using chain transactions, nothing can happen in between, right?
So his question is, if you're using chain transactions, then nothing can happen in between. In the case, so say I have n tuples. Each guy updates that one tuple. So what will happen is T1 will execute, updates tuple number 1, commits, releases the locks for that tuple number 1. The next guy runs, he can update tuple number 2. We're not holding a lock for the first guy, right? So what's nice about compensating transactions, or sorry, the SAGA transactions, using these compensating transactions, we don't have to maintain any extra state in the application about where we are in the scope of the execution model or the workflow. So now I'll say I don't think any major database system supports this. Well, you'll see SAGA transactions or SAGA workflows in a lot of like high-level application servers, right? Like I know like in .NET has something like this where you can do these kind of operations over a large database, and sort of the application server will maintain the stuff for you and work in conjunction with the database system. So I don't know whether this is actually made into any real system, but this is the base. This is probably the best approach to doing bulk updates. Yes.
If some other process or application deletes the first tuple before you get back to C1.
So the question is, if we update T1, the first tuple here, and then we get to this point here, and we got to roll back, but in between that time, someone comes along and deletes the first tuple. Not in chain transactions, I don't think.
Not in chain
Yeah.
So would your compensating transaction have to deal with?
Yes, you have to deal with that. Yes. So you could do something like if you're using, yeah, you could do different recursive schemes like multi-versioning. You go back in time to get back the previous state of the database. I'm not saying this solves all the problems, but this allows us to be able to do those bulk updates without having to hold locks the entire time or take the database offline. Right? I think this is sort of the best approach we have sort of now. Yes.
So, as a trade-off, because we're not maintaining state, but we have to do more work.
When we say we have to do more work,
At the database systems.
the database system has to do more work. Yes.
So that's the
What's wrong with that? Right? No, I mean, so one of the overarching themes will be of this course is the average application programmer is not the sharpest tool, right? The database system developer is always going to be a person that knows the ins and outs of the system and can probably do a much better job executing transactions than your average JavaScript or Ruby programmer, right? And Google even admits this, right? So when you read the Spanner paper, they talk about how when they were using Bigtable and they had these eventually consistent database systems, all their application programmers were spending all the time writing logic in the application to deal with inconsistent data because the database system was not providing transactions. So they say it's better to have a small cabal of really smart people who take a database course like this, who know actually how to write transactions very efficiently. It's better to have them make the system go faster than have everybody else spend their time trying to deal with a database system that doesn't have transactions. So I have no problem saying, yes, it's more work for us as the database developer, but absolutely, yes. But we can do a better job.
I don't mean as a developer, but the system has to now do more compensating transactions.
Absolutely, yes, it has to do more work. That's fine. But again, that's like, think about it. It takes more work as a development, it takes more resources on the database side, but the database system has the complete view of the data, and we don't have any worry about any inconsistent state that may be maintained outside in the application, right? The database system already has recovery methods, already has recovery protocols. We know how to recover things after a crash. If you maintain state in the application, you have to write your own write-ahead, you have to write areas yourself, and people are probably going to get that wrong. So this is fine. All right, so let's look at a quick example of how SAGA transactions work. So again, this is our counter example. We'll do A plus 1, B plus 1, and we'll do transaction chains from one to the next. We get to here in transaction 3, it updates C, it adds 1 to it, but then our system crashes. So we'll execute the compensating transaction for this guy and this guy. And again, this is just decrementing at a logical level the changes or modifications that were made during the chain transactions at the top. So we're not really going to discuss SAGA transactions or these transaction models other than the nested ones and save points throughout the rest of the course. But I think it's for your own general edification. I think this is important for you guys to know that when you go out in the real world or deal with other sort of more complex systems, that there's other models that are available other than just flat transactions. Yes?
So in the chain transactions like these, logically, I mean, in a serialization order, nothing gets inserted between any of these, right?
So the question is, in a chain transaction, Nothing can be inserted in between here. Yes, if you're trying to have serializable order, yes, if you want that isolation level. Okay. So in the sake of time, let's sort of keep going. So now that we sort of have, from this point on, and probably for the next 2 classes, we're mostly going to focus on the flat transactions, right? Because again, these are probably 99% of all applications that are out there are using flat transactions rather than the more sophisticated models. So the protocol that the database system is going to use to allow multiple transactions to run simultaneously in a correct manner is its concurrency control scheme, right? And the basic idea of a concurrency control protocol is that it wants to provide the illusion for each of the transactions that's running at the same time that it has exclusive access to the shared database, even though it doesn't. Now, when we talked about disk-based database systems, we said that we were going to use concurrency control to allow simultaneous transactions because at any time a transaction could try to access a record that wasn't in memory, and it therefore would have to stall while it would fetch that page that it was on into the buffer pool. But now, if we assume we have an in-memory database, we're never going to have disk stalls because of this, because everything's always in memory. And therefore, the concurrency control scheme is not providing us with concurrency to allow other guys to keep running when we have to stall. It's going to allow us to take advantage of all the extra cores that the CPU manufacturers are providing us. Right? So essentially, the era of ratcheting up the clock speed on a single core in CPUs is over. And the only way that Intel and AMD and the other chip guys are going to be able to get better performance is that now they're going to provide us with more cores. Right? So Intel announced that the Knights Landing CPU, I think, is coming out this year, and that's going to be in a single socket CPU with 72 Atom cores. Right? So you're not going to be able to ratchet up higher gigahertz because at some point the silicon melts. So the only way we're going to get better performance in our database system is if we can use these extra cores and allow for extra parallelism in the system. So now our concurrency control scheme is not so much involved in allowing transactions to keep running when one guy stalls. It's allowing us to execute on as many cores as possible and have the highest amount of parallelism as possible, but then still maintaining correctness in the system. And so the goal for a concurrency control scheme is that we want to have the effect of a group of transactions that executed at the same time to change the state of the database in such a way that it would be equivalent or the same as if the transactions executed serially one after another. So we're going to allow transactions to run on multiple cores exactly at the same time, but we want the state of the database to be the same as if we executed them, not concurrently, but one after another. And so you can think of the concurrency control scheme as going to provide the atomicity and isolation guarantees in the ACID acronym. So one of the 3 things that the database system is going to maintain internally for each transaction is what we'll call its internal transaction state. And so there's the undo log entries, and these are going to be all the original values of any record that it modified in the database system in case it needs to roll back to it. And we said before that we don't need to store these on disk anymore because when a transaction commits and we write an acknowledgement back to the application to say you're done, we haven't written any dirty pages on disk because everything's in main memory. So therefore, we can immediately just drop all the undo changes we have because we know we're never going to have to roll it back once we finish it. Then we have the redo entries, and this is essentially the modifications that the transaction did make to the database. We do want to write to the redhead log because it could be the case that our system will crash before we take a next snapshot and be able to write the state of memory out to disk. So we need to store these in what's called the tail of the redhead log, and then when the transaction finishes, if we have a strongly consistent system or we want a synchronized system, we have to do an fsync and flush the log out the disk before we send back the acknowledgement to the application. And then the last piece is the read and write set of each transaction. So the read and write set are the identifiers of the tuples that the transaction has either read or modified. And the reason why we need to keep track of what tuples it read because we want to make sure that it doesn't read something that it shouldn't have because some transaction that came along in the future or in the past wrote something that we missed or shouldn't have read. And so what information we're going to maintain for, I would say, for the read-write set as well as the undo set really depends on the concurrency control scheme, right? So in the case of like multi-version concurrency control, you just need to store pointers to the tuples that you modified and then at what timestamp you expected to see there. In the case of like two-phase locking, you need to maintain all the locks you may be waiting for and the locks that you currently hold, right? We're not really going to talk in the details of this, but just realize that every time you start a transaction, there's all this extra stuff that it's using on the inside to figure out whether your transaction is actually running in the correct order or not. All right, so now, in general, there's two main categories for concurrency control schemes, and you saw this in the paper that you read. And I will say this, that I've had people come tell me that they have a concurrency control scheme that does not fit into these other two categories, and anybody who tells you this does not know what they're talking about. These categories are not something I made up. Like, this is something they developed in the early 80s, late 1970s. Basically, every single concurrency control scheme that exists has to fall into one of these two approaches. So the first group is called two-phase locking. And so these are pessimistic schemes where the database is going to assume that conflicts will occur. So it's going to require all transactions to acquire locks for any item that it wants to read or write. And then it's going to have to figure out how to resolve deadlocks in some manner later on. Timestamp ordering, these protocols are optimistic schemes where it assumes that conflicts are going to be rare, and therefore it doesn't require transactions to maintain locks. And it's just going to check at commit time whether there's any conflicts. So you allow the transaction to run as long as it can, do as much work as it can, where you know there's not going to be any conflicts. And then when it goes to commit, then you check around and see what was going on at the same time and see whether you need to roll anything back. So we'll go through both of these examples in a second. So two-phase locking is essentially what you learned in an introduction database class, right? It's not really that fancy. And so we have an example here of a transaction. It wants to do a read on A and a write on B. And again, under the two-phase locking protocol, we say that it has to acquire the locks for those objects before it's allowed to do anything. Now, in this case here, I'm being vague on what A and B actually are. Right? They could be tuples, they could be pages, they could be tables, they could be databases. It doesn't matter. The two-phase locking protocol essentially works always the same way. So the first part here is called the growing phase, right? Because this is where the transaction is allowed to acquire locks, as many locks as it needs. And then the second part is the shrinking phase. And this is where the transaction starts to release locks back to the database server, right? Once you enter the shrinking phase, as soon as you release one lock, you're not allowed to acquire any new locks. Right? If you try to do that, the database system will abort you and you have to get restarted. You have to acquire all the locks you need in the first part here. So if anybody took 615 with me last semester, can anybody tell me what the difference between regular two-phase locking and strict two-phase locking is? Yes?
Strict two-phase locking to get all the locks at the beginning?
Not necessarily.
Okay.
So his statement was, in strict two-phase locking, you have to get all the locks at the beginning, and that's not necessarily. Yes?
You release all the logs together.
Right. Strict two-phase locking is when a transaction, you only release the transactions until at the very end. So in this case here, this transaction, it released the first lock on A, but before it releases the lock on B, it's allowed to do another write on B. In strict two-phase locking, you wouldn't be able to release these locks and interleave them in operations. You have to release everything all at once. Strict two-phase locking is guaranteed to provide serializable ordering or serializable schedules. Regular two-phase locking, it doesn't necessarily guarantee that. So in this case, in this paper you guys read here, they were running with a strict two-phase locking protocol. So now, say we have another transaction that comes along, and say these two guys land on the machine exactly at the same time. We have two cores, so they can run simultaneously at exactly at the same moment. And so we'll use these arrows to indicate the program counters. So they both start at the same time. This guy wants to get a lock on A and assume that no other transactions run at the same time, so therefore it's allowed to do that. This guy wants to get a lock on B. Nobody else is running at the same time, so it's allowed to do that. Then they go forward, and he does a read on A, which is allowed to do because he has a lock. He does a write on B, which is allowed to do because he has the lock. But then we come to this part here. This guy wants to get a lock on B, but that lock is being held by transaction number 2. So therefore, it has to stall and wait. This guy wants to get a lock on A, but that's being held by this guy, and therefore he has to stall and wait. So what is this? Deadlock, right? So what will happen here is the database has to figure out something's not right. I got to abort one of these guys and try to free up all these locks. So the way the different two-phase locking protocols differentiate with each other is based on how they're going to deal with deadlocks. And within that, there's two categories. The first is called deadlock detection, where this will allow transactions to wait to try to acquire a lock, but then in a separate thread in the background, we're going to examine the waits for graph of the different transactions and try to identify cycles. Right? This graph would be a list of all for every transaction, what other transactions they're waiting to acquire the locks from. So if you see that there's a cycle, the deadlock detection thread will use some heuristic to pick which transaction it should kill in order to break that deadlock. In deadlock prevention, when a transaction tries to acquire a lock, it will run some protocol to figure out whether that, if that lock is not freed, right, if that lock is available, then it can acquire it right away. If it's not available, then it'll figure out whether to allow the transaction that's trying to request the lock to wait, assuming that the other transaction that's going to hold it is going to finish up soon, release it, and be able to acquire it, or whether that transaction that is waiting should kill itself right away because it assumes that the other transaction is going to take a long time, and therefore we don't want to stall and wait and hold all the locks we already hold. Or it can decide to kill the other transaction that already holds the lock and let our requesting transaction steal it. And again, for these different protocols, the different commercial database systems all do different things. There's not one heuristic that is better than another. Again, as in many cases in database systems, it depends on what the workload is, right? There may be some heuristic that works better in some scenarios, and another one might work better in others. Okay, so let's talk about timestamp ordering. So what I'm going to show you here is the basic timestamp ordering protocol. It's called the basic TO in the paper. On Monday and Wednesday next week, we'll talk about the more advanced or more modern versions of timestamp ordering, MVCC and OCC. But the basic idea is somewhat the same. So now under timestamp ordering, instead of having the transaction acquire locks, we're going to assign it some kind of timestamp that we're going to use to figure out what order it should be allowed to execute. What order should we commit them and have and update the database state. And so you can think of this as one thing. It could be like the wall clock. It could be a logical counter. There's a bunch of different ways you can use, different methods you can use to generate a timestamp. So in this case here, we'll say this transaction just gets timestamp 10,001. So inside our database system now, along with each tuple or each record, we're also going to maintain the timestamp of the last transaction that read it and the last transaction that wrote to it. Right? So we'll assume in this case here, there's no other transaction running right now, and the initial timestamps for all these records are just 10,000. So now when we start a transaction, it wants to do a read on A, and then we'll update the read timestamp here. This guy does a write on B, and then same thing, we update the timestamp here. So now we'll say in this middle part, the transaction is going to do some additional processing. It's not going to execute any queries. It's not going to do any modifications to the database. It's just going to sit and crunch something, right? Compute pi. Doesn't matter. But during this time, some other transaction started running, and it modified this record A, and it updated with its timestamp. And this transaction started after our guy did, so it's going to have a higher timestamp. So now when our transaction comes out of the stall and now wants to do the write on A, it'll see that the write timestamp is in the future from when it started. And therefore, it can't write to this because it'll be overwriting something that occurred in the future. And in this case here, the database system will recognize that this would violate serializable order, and it'll have to abort this transaction. So I would say, so again, this is what we're calling the basic timestamp ordering protocol. This is what is in the textbook when you read timestamp ordering. Right? This is the basic approach that we usually teach in the intro class. I will say that again, as far as I know, no real database system actually implements this. They usually implement OCC or MVCC. Okay, so in timestamp ordering, again, that was the basic timestamp ordering protocol. We'll discuss more about MVCC and OCC in next class. But the basic idea of MVCC is we're still going to use timestamps to figure out how to order things. But every time we modify a tuple, rather than just writing over the original one, we'll create a new version in the database with a new version ID that corresponds to our timestamp. And then any transaction that comes after that, comes after our transaction, we'll be able to read our modification. In OCC, instead of having new versions or updating the global database state, we'll make all our changes in a private workspace for our transaction that's not accessible or cannot be read by any other transaction running at the same time. And then when our transaction commits, then we'll go look around and see whether there's any conflicts. And if not, then we'll apply all our changes in the private workspace into the global shared database. And then it becomes visible to everyone else. And again, we'll discuss more about this next time. All right, so in general, in the paper, there's the 6 concurrency control schemes we're going to look at are these, and we're using these abbreviations to signify them. So here's the two-phase locking ones, deadlock detection, no wait, and wait and die. So these two guys, the prevention ones, and the top one is the detection one. So these algorithms here, these concurrency control schemes, are used in these real database systems. DB2, MySQL uses a variant of MVCC and 2PL, which we can talk about later. But SQL Server, Sybase, SQLite, and QRID, all of these guys are using two-phase locking. And then for timestamp ordering, we have the basic protocol, MVCC and OCC. And I would say that these protocols are more common now in the newer systems. Most of the new systems that have come out that support transactions in the last 5 years or so are going to be using probably MVCC or timestamp ordering. But of course, Oracle and Postgres are probably the two most famous ones that came out of the 80s that started with this. Okay, so for the paper you guys read, we used we wanted to evaluate all these different protocols and see how well they scale up on CPUs with a large number of cores. And we couldn't just use MySQL because we had to make major changes to the system to be able to run all these different algorithms. And there's all these additional features in MySQL that would slow things down. And so obviously also you can't buy a CPU today that has 1,000 cores. So we're using a chip simulator that was developed at MIT called Graphite that can scale across a cluster about 20 to 30 machines and can simulate a single socket CPU that has 1,000 cores. And so this CPU that we're using is not going to be sort of the NUMA architecture that you guys are maybe familiar with in like Nehalem chips and Intel chips today. It's using a tile-based architecture where every tile is a single core, and there's sort of a 2D mesh network that allows one core to communicate with another. Right? So it's sort of a NUCA architecture. Right? It's a non-uniform cache instead of a NUMA architecture, a non-uniform memory architecture. The one thing to point out is that part of the reason why we had to write our own system is that the chip simulator is really slow. It runs about 10,000x wall clock time. So if you have an application or some kind of process that is going to take a minute, when you run it in the chip simulator, it's going to take 10,000 minutes. Right, so we had to write our own system from scratch because there'd be all this additional stuff that would slow us down and cause the simulations to take forever. Like the student that worked on it with us, he wrote assembly in the system to make it really go as fast as it could. Right? He was really hardcore about it. So the workload we're going to talk about for this class is called YCSB, or the Yahoo Cloud Serving Benchmark. So this is a benchmark we'll see over and over again in a lot of the papers that we read. So this is a benchmark that was developed by researchers at Yahoo Labs in around 2007, 2008. That was designed to be emblematic of a lot of the cloud platforms, the cloud applications that they were deploying at Yahoo at the time. And now it's being used in a lot of different research environments, research projects. So we'll have about a 20 gigabyte database, and for each transaction we'll execute, it'll modify a random 16 tuples. And the access pattern of these transactions will be based on a skew distribution. So that means there'll be some hotspot in the database where most of the transactions will do all the reads and writes to. And this is very common in real-world applications. There's usually a lot of skew. And when you're running all of the transactions in our benchmark using the serializable isolation level. Again, we'll talk about isolation levels more in next class. But again, the main thing about serializable is that the end state of the database will be the same as if the transactions were executed in serial order, even though they were interleaved. Okay, so for the first experiment, what we want to do is we want to see what's the upper bound of what these different concurrency schemes can do when there's like no contention whatsoever. So we're gonna execute a workload with uniform distribution, meaning any tuple is accessed with the same probability as every other tuple. And we're not going to do any modifications. So all the transactions are just going to do reads. So again, this would be the best that these systems, these protocols can do up to 1,000 cores. So the first trend we see is that the deadlock detection scheme and the no-wait scheme actually perform the best. Right? They're not scaling linearly, but they're doing much better than the other ones. The second thing is that we see that there's a sort of knee here for MVCC and no-wait of roughly around 9 million transactions a second when we get up to 800 cores. And what this is going on, this is the bottleneck caused by generating unique timestamps for every transaction. We'll see in a second, but essentially we're using, again, an atomic counter, and the best the system can do is up around 9 million. And then the last one is that we see OCC actually performs the worst here, and along with timestamp. And part of the reason what's going on here is that because every single time you access a tuple, even though you're doing a read, even though nobody else could ever modify it, the protocols have to make a copy of that tuple to ensure that if they go back and try to read it again, they won't read a different value. So you'll be able to ensure repeatable reads. So what's essentially going on here is that it's all the memory copying and that is preventing this thing from scaling. So now we're going to add in writes. We're going to add in contention. So for this is going to be 50% of the operations per transactions will modify the database. And the access distribution will be such that 40% of the transactions will access just 10% of the database. So we have a 10% hotspot in the system. So now we see the first trend is that before, deadlock detection was doing the best, and now it's actually doing the worst up to 1,000 cores. I should also say, for every single core we add, we're adding another concurrent transaction. So this is essentially 1,000 cores has 1,000 transactions running at the same time. So deadlock detection is doing the worst because there's so much contention on this hotspot in the system that there's all these deadlocks, there's all these backlogs of these lock requests, and therefore the deadlock detection thread is just aborting transactions left and right, and they're not actually ever getting any useful work done. The second we see is that the no wait and the wait and die approaches actually perform the best, and this is because these are lightweight protocols that are really simplistic, and there's almost no overhead of maintaining transactions. And because this is an in-memory database, the cost of aborting a transaction when we have a conflict is really cheap, right? I made maybe 5 changes in memory. I need to abort my transaction. I roll it back. I just reverse those 5 changes. That's 5 memory writes, which can be done very, very efficiently. And then the transaction gets requeued. And in the middle here, we see that the timestamp schemes are roughly performing about the same. And this is you can account for this overhead due to the cost of doing writes into memory, because we're not doing in-place updates. So like in a case in like MVCC, every time you do a write, you create a new tuple in the database. Timestamp will do it on every read, and OCC does it on every read and write. All right, so now we get to the extreme case where we have, again, a write-intensive workload, but with high contention. So now we have 60% of the transactions are trying to just access 10% of the database. So now we see is that over here at 1,000 cores, everything falls apart. There's this weird dip in the knee of no wait, and this is strictly due to just to lock thrashing, where the locks are transactions are just waiting forever to try to acquire things that keep aborting and aborting and aborting. The other interesting thing to point out is before, when we had a small number of cores, OCC was actually doing the worst, but now it's actually doing the best. And the reason why this is occurring is that the way OCC works is that it guarantees that one transaction will always be able to commit because it's going to do validation in serial order. So it's essentially running, even though we have 1,000 cores, it's running at the same speed as it would with a single core because one transaction is always allowed to finish, right? And then all the other cores are just rolling back and doing wasted work over and over again. So now the other thing I want to point out is here we saw at 1,000 cores, everything falls apart. But then we seem to be scaling up okay around 32 cores. This is essentially where the state of the art is right now in database systems, right? Most, when you buy a machine from Dell or whatever, you're probably going to get roughly about 32 cores. And so most database systems today can scale up quite well. It's sort of this middle part here that is uncharted waters where we don't really know how to make things work better. And so I say this is sort of the main part here that we're sort of focusing on in our research to try to figure out how to get this to scale. We're not going to be anywhere near this number of core counts in the future, and we're kind of okay here, but going beyond this, we think there's going to be problems. So this is sort of ongoing research that we're doing to try to solve this problem. And so one of the things we can also do is we can also look to see, well, what's going on in these database systems that's causing them to not be able to scale up? Why are things getting worse? And we instrumented the database system to allow us to measure how much time is spent in different parts of the system. And what you see are these yellow splotches here is all the overhead due to transactions that cannot commit, and therefore we have to roll back their changes and restart them. So we see in the case of OCC, all the cores, except for one of them, is just aborting and aborting and aborting transactions over and over again. You're never actually making any forward progress, right? And in the case of timestamp, we see that it's waiting a lot of time to get access to things and copy data, and therefore that becomes lock contention on the latch contention on the database system itself, and that's what all this blue spot goes toward. So basically, you're seeing the red part is actually the useful work that these systems are doing here, and it's not that much because there's all this overhead of concurrency control that's slowing us down. So let's talk about the bottlenecks, and these are applicable, I think, for today's systems. Even at smaller core counts, you still can have these kind of problems. And so I sort of highlighted here for each of the 3 problems what protocols are inhibited by them. So the first one is lock thrashing. Lock thrashing is this concept where as the amount of contention or concurrency increases in the system, the time it takes for a transaction to acquire the lock that it needs starts to grow. And therefore, any locks that it holds, now it holds those for even longer because it's trying to acquire the next lock. So the transaction that's behind it that's trying to acquire the locks that's held by the first guy, they have to wait even longer. And this sort of builds up until you have so much contention that performance actually starts to get worse even though you increase the number of cores that are available. And so we can measure this phenomenon by running a workload where we have no overhead due to the deadlock prevention or deadlock detection scheme in the system. And we can do this by requiring the transactions to acquire all the locks that they need before they start running, which is sort of the example he brought up. And we're going to require the locks to require the transaction to acquire the locks in primary key order. So there can be no deadlock because I'm always going to try to acquire the locks in the same order, and therefore nobody else can be waiting for transactions. I won't be waiting for a lock held by somebody else who may be waiting for my lock. And so we can run this in our system with the three different skew levels. So no skew, medium skew, high skew. And what you see is that these knees here, as you scale up the number of cores, that correspond to lock thrashing. So at these knees here, these plateaus, the convoy of transactions that are waiting to acquire locks gets so big that performance actually starts to degrade. And what's actually really cool about this experiment is if you look in the textbook that discusses lock thrashing, you'll always see this kind of like simulated graph here that looks like this, right? And you always see this knee concept, or this knee trend. And that's exactly what we see when we run in the real system, right? So this is kind of cool. This is showing that, like, stuff in theory actually works in practice. The next problem we have is the timestamp allocation. So again, in timestamp ordering, all the transactions have to be provided with a new timestamp. In the case of OCC, it's provided at the end. In MVCC and basic timestamp ordering, it's provided in the beginning. But this now becomes a hotspot in our system because for every transaction that shows up, we have to increment this timestamp counter and give it to the next guy. So in this list here, in the paper, we examine a bunch of different ways to allocate timestamps, and we're sort of going from worst to best. So the mutex is what everyone pretty much will do if you try to write the timestamp ordering out protocol the first time. It's basically you have a single counter, you protect it with a mutex, and anytime you want to update it, you have to enter the critical region and update it and then release the locks. And this is the worst possible thing you can do because acquiring a mutex is really expensive. The next best approach is to do an atomic addition operation. So this is, again, you have a shared counter, and anytime a transaction wants to get a new timestamp, you update that counter by 1. And the problem with this is that that counter is going to be shared across all the cores, and every time you do the update, even though it's an atomic operation or atomic instruction, and therefore it's really fast, you have to invalidate the cache counter across all the different cores that are using it. So what happens is if you have, say, 1,000 cores, one guy updates the counter, and then you have to invalidate all the 999 different cores so they don't try to get the same value again. And that adds a lot of traffic to the internal chip network, and that slows things down. A better approach to get around this is to do batch atomic addition. Basically, instead of every time you want to get a new timestamp, instead of telling the counter add 1 and give you back the timestamp, you say add 10 or add 100, get back a batch of timestamps, and then your core, as it executes transactions, just hands out the next guy after another and doesn't go back to update the counter until it runs out of its batch. This has problems, though, because if you have a protocol where if a transaction has to abort because its timestamp is lower than some other timestamp that updated the tuple, then you will burn through all your transaction IDs in that batch before you realize that I have to go back into the counter and get the next batch to get above that and allow the transaction to run again. And then you can use a hardware clock, and this newer Intel chips have this, where it's a single instruction to get a synchronized timestamp register that's maintained across all the different cores. Right? So the hardware will maintain the clock and all the different systems to keep everything in sync. So now you just read this one register, and you're guaranteed to get back a monotonically increasing timestamp. And then you append the core ID, and that'll be guaranteed to be unique across all cores. The problem with this approach is nice, and it actually makes a big difference. And again, newer Intel chips have this, but not all CPUs have it. Not AMD ones don't have this. ARM doesn't have this. And it's not clear whether this will exist in the newer CPUs that come out later on, because it's really expensive to do this synchronization across a lot of different cores. And the last approach is not something that exists in existing chips, but the student implemented this in the simulator, and that's having a special hardware counter actually inside of the CPU itself that's sort of at the center of the die. Then if any transaction that wants to get a new timestamp, you send a single instruction to get the new value from the counter, and it gets automatically updated. And this turns out to be a really good approach, but again, the problem is this doesn't really exist in any systems. Yes?
How is it counter hardware
How would you
better than the clock?
So the question is, how is a counter implemented in real hardware better than the clock? Well, it turns out, actually, when you run the experiment, it's not. I don't know exactly how. What's that? This is in the simulator. Correct. Yeah, this is the simulator. So your question is why would the hardware clock be better than the counter?
Or vice versa in silicon.
Right. So I'm not an architecture person. My understanding is that the way the clock works is it sends an update automatically to all the cores every time there's a new tick, right? So when you do a read, you already have the correct time right at your local core. In the case of the counter exists at the center of the chip die. So to read it, you have to send a message to the center, then you get the new value back.
So it's not replicated.
It's not replicated, yes. Does everyone understand that? Again, this is all sort of, not theoretical, but this is all sort of done in simulations. It's not really in real hardware today. But the clock actually is in Intel chips today. But when we talk to them, they are like, yeah, that may not exist in the future, so they don't rely on it too much. Okay. So in this experiment here, we're just showing how these different things scale. So basically, we'd have, at each core, we'd have a single thread to keep allocating timestamps as fast as possible. And you see at the bottom, the mutex plateaus, does the worst, followed by the atomic addition. The batch guide is a little bit better, and then the clock ends up being the best. And so for our experiments from this paper, we end up only using the atomic addition because this is what is actually usable in existing systems. The atomic batch one works for some protocols and doesn't work for some other protocols, so we decided to just use this one because it was sort of had uniform performance across all the different schemes. But we'll see this when we talk about Silo, its version of OCC next Wednesday. They're using the atomic batch approach. All right, so the next bottleneck is memory allocations. Again, in the case of timestamp ordering in MVCC and OCC, every single time you do a read or write, you have to copy the tuple and insert it into the database. And this starts to add contention on the memory controller for all these different updates, and that's why a lot of these systems have to slow down. We also found that the default libc malloc that sort of comes with Ubuntu when you download it is actually really slow and ends up being a bottleneck. So this is why most systems don't, most real database systems don't use the default libc malloc. You use like TC malloc or JE malloc, more optimized versions of it. In this case here, the PhD student that worked on this project wrote his own version of malloc without telling me. And he was able to get just the same performance as JE malloc and TC malloc, right? And we can talk about different memory allocation stuff later on. But in general, again, if you ever build a database system, don't use the default malloc. Okay, so we have like 10 minutes. I'm gonna go through this really quickly. There was a seventh concurrency control protocol scheme in the paper that you've read about that I haven't discussed yet. And this is it went by the name HStore. So this was based on the work I did when I was in grad school. It's now commercialized in the system VoltDB. But the original idea of the HStore concurrency control protocol didn't come from HStore. It actually, the paper you read from Hector from last week, he talks about doing coarse grain locking or coarse grain partition locking for transactions in 1992. And that's essentially where this idea came from. There's another system that came out of NYU called K or KDB, which is actually used a lot in Wall Street, that does the basic same approach. The basic idea is that instead of maintaining multiple versions, instead of having transactions acquire locks for individual tuples, we'll do coarse grain locking based on partitions. So even though we're talking about locks, this is still a timestamp ordering scheme. So the idea is that we're going to split the database up into disjoint subsets called partitions. If you come from a NoSQL background, shard is essentially the same idea. And then for each partition, we're going to assign it a single-threaded execution engine that has exclusive access to the data at that partition. And what that means is that if any transaction wants to read or write data at that partition, it has to first acquire the lock for that partition before it's allowed to start running. And the way we're going to implement this locks is that we'll have a single queue per partition, and we'll order transactions in the queue based on the timestamp of when they arrived in the system. And when a transaction reaches the front of the queue, it's allowed to start running in the engine, and it knows that no other transaction is running at the same time. So therefore, it doesn't have to do any of the low-level locks and latches on the data structures or the data itself, because no other transaction could cause a conflict. If a transaction tries to access a tuple that's not in the partition that it's running at and has a lock for, the database system has to abort it, roll it back, and re-queue it in both of those partition queues. So if I need to touch multiple partitions, I have to have the locks for those partitions before I'm allowed to start running. So now when we look at run the HTTP protocol with all the other ones, we see that it performs significantly better, right? So this is the read-only workload for YCSB, and the reason why we're doing read-only because that's again the best case scenario for these other concurrency protocols. And what we see is that it scales up really well up to around 9 million transactions, but then we sort of hit the same timestamp bottleneck that the other guys do. And again, the reason why this is running so much faster is because it's not doing any low-level locks and latches. Every transaction only has to touch data at one partition. It reaches the front of the queue. It runs without any stalls to completion. Right? It's almost running at bare metal speed. And then it finishes and commits, and then it's done. So as long as your transactions only have to touch a single partition, this runs really, really, really fast. If you have to have multiple partitions, then things start to fall apart. Right? So in this case here, the yellow line is what we saw before, when a transaction only has to touch one partition. But then we have 2, 4, and 8, and 16. And what you see is the performance basically flatlines. So this HTTP protocol does amazingly well for the single partition cases, but if you have multiple partitions, it doesn't work well. And when would you have something that has multiple partitions? Well, certainly if you're doing any kind of analytical query or analytical transaction, you're going to have to touch basically the entire database, the entire table. So therefore, you would have to lock all the partitions while you do this analytical query, and that would back up all the other transactions that want to update things because you can't run them at the same time. So the HTTP protocol works very well for a sort of a certain class of applications that are very common in real-world scenarios, but it's not certainly general purpose, and it's not something that can handle all different situations like MVCC does. Okay, so to finish up, we'll see this more next week, but the main takeaway from all of this is that concurrency control schemes are really hard to implement in terms of both correctness and high performance, right? Because there's a lot going on, and as you increase the amount of concurrency in the system, it's really hard to balance all these different needs, right? And so a lot of the commercial systems that have been around for a while, they have a lot of legacy code that it sort of inhibits performance, and you sort of have to take a fresh approach, and we'll see this next week, in order to get scale up and support the high core count that we have today. The other thing to point out is this evaluation is interesting, but we did this about 2 years ago, and now there's a big focus on the hybrid workloads, the hybrid transaction analytical workloads. So all these workloads I talked about, they're just doing reads and writes on a small number of tuples. If you actually want to bring in workloads that do the reads and writes plus the analytical and machine learning stuff at the same time as you're updating the database, then that's a whole different ballgame, and therefore a lot of the findings that you can extrapolate from these graphs may not be applicable to these newer applications. Okay, so we're done for today. Starting on Monday, we'll start off talking in the beginning about isolation levels. So we'll go a little bit deeper and beyond what we teach in an introduction course. We'll talk about serializable snapshot isolation. And then we're going to talk about modern MVCC protocols, modern multi-version concurrency protocols. The paper you've been assigned to read, I think, is a really good example of one of these new multi-core in-memory database concurrency protocols. And it's actually from the Microsoft research guys. The paper is the concurrency scheme for Hackathon. It won't say Hackathon in the paper because the marketing guys wouldn't let them to use the term in the paper when it was published. And then later out it came out and everyone understands that's the Hackathon paper. So when you read it, understand that this is actually the real concurrency protocol that's being used in SQL Server today for the Hackathon storage extension. Okay? And I think the Microsoft research guys do some amazing stuff for databases. There's another paper that's optional for Deuteronomy. It's another system that this guy's developed. All right, any questions? All right, guys, see you on Monday.